I hope you rested well during the course of the night, and that you also started the day successfully. And you have been enjoying, I hope so, and I wish you a good to have a good time with me during this session. Okay, so last time when we parted, we stated the theorem about the expansion in terms of cosine and sine. We saw that if the function f of x, which is periodic and of period 2 pi, is piecewise continuous over the interval, obviously when you say piecewise continuous, it's piecewise continuous over the interval negative pi, and then you extend it periodically all over the real line. That is, you take that picture and you shift it by 2 pi throughout to the right and throughout also to the left. It gives you the full picture, and if you look at that global function, you will see that there is discontinuity at negative pi, and they are multiple. When I say multiple, that will be odd multiples of pi and negative pi. At odd multiple, you will see that there will be discontinuity. So such a function is called piecewise continuous. So it's not globally continuous. That is, from one end to the other, you can draw without lifting the pen. That's not the case. It's only continuous in a sub-interval. Like negative pi, you can see you can draw from negative pi, from negative pi to pi, you can draw everything. Now, when you move from that, there will be a discontinuity. So it is called piecewise continuous. So if the function is piecewise continuous, similarly for the derivative, therefore, of course, when the derivative piecewise continuous, and also you have the left and right derivative, right? That is, at each point, the left and right derivative exists. Therefore, the function is, the series itself, S sub f of x will convert to f of x at points of continuity. That is, for instance, for any x is in the interval negative pi, the function will converge. The series S sub f of x will convert to f of x. There will be convergence. Let me write it down. What I'm saying here is that since we have our function, this one, S sub f of x, this is our series. This is the Fourier series. Right. Okay, now, if the function f satisfies the condition of the theorem that I just mentioned, therefore, this function will converge to it will converge when? Yeah, it will converge. This will converge. Right. That is when you say converge, actually it means that this will be equal to that. It will converge. It will converge to this. So they will be equal because this is already a sum, right? Or we can say S sub n. That is the partial sum. When you take n to infinity, it will converge towards that. Okay, this will be for any x point of where f is continuous. For any x point of continuity. Point of continuity. Okay, now this will converge to at point of discontinuity. This one. Okay, so this is what we saw from the theorem. So in other words, either we have this expansion, f of x equal to the Fourier series, or we have this. So this is the average. Because if you are at a point of discontinuity, let's say for instance, okay, so let's say for instance that this is our axis, and then this is a, x equal to a. Okay, now this function, let's say, okay, let's say the function is like this. Okay, so let's say that our function is this, right? So let's say that this is our function. And now on the other interval, it will be like this. So you see that I shifted this periodically. I take that, I shift it by the period. I translate it by the period, and that's what I get. You can see that here, this is a point of discontinuity. And at this point, f of s will be equal to this. So this is an average value. So this value is somewhere here in the middle. Actually, that value is here. It will be here. So this value of the function is here. This average, this one, is here. And now this value of the function and this one this is f a plus, right? Because we are on the right of a0, so that's a plus. This will be the value, and this is that one is f of a minus. You see that a plus and a minus are different. That's why we say it is discontinuous. Because if the function were continuous at this point, these two will be equal. And you can see that if these 2 points are equal, this average will be equal to f of a. And which is the case here when x is a point of continuity. I hope it is clear for everybody. So that's what happened with Fourier series, because we are dealing with periodic functions. And at the end points of the interval, generally, they are discontinuity. And when you extend periodically, you have a behavior like this one, where you have point of continuity here, or here, these are points of continuity, but here we have a point of discontinuity. So this is very, very, very important to understand. All right. Okay, so I hope it's clear now. Of course, if the concept was not that clear, I hope that by explaining this way, some of you understand better. Right? It's always good to repeat many times until the concept sink into the brain. Even if you eat what? You know the food. I will not mention that food. Anyway, regardless of the food that you eat, anyway, food is there for your good, to give you strength to study hard. But I like mahango anyway. I like it. All right. So that is it. Now, the next thing before we parted, we stated the theorem about cosine and sine. We said that now, if this function, f, is an even function, let us look at that. Okay, this is a proof. Okay, I tried to write the proof. I asked you to use this change of variable. So if you use that change of variable like here, you see that it will give you negative, that integral. And you add this with this one, it gives you 0. So this is an elementary mathematics problem that each one of you should be able to do. All right. Okay. Let me copy this like that. And paste it here. Okay, now if our function if f is an even function, we know already that s sub f of x, how do you write this? A0 by 2 plus the sum kn plus bk sine kx. So this is our Fourier series. And we saw that if this f satisfies the condition for the convergence of this, because this sum can be infinite, right? It can be infinity. This one can be infinity. It is possible that you have infinity. That would be divergence, right? Okay. It's just a series. It can converge, it can diverge. Okay, now when f satisfies the condition of the theorem at the point x, then we can have f of x equal to that. So if there's convergence, you have f of x equal for the expansion, right? Convergence, when there is convergence. When there's convergence, we have this equality. Right. Okay. Now you can see that if f is even and you still have this summation, it will not work because f being even means that for any x, of course, in the domain of f, let me call it df. Of course, the negate of that is still there, so I will not write that. So we have f of negative, f of negative x is equal to negative f of x, like that. Now, if you write it here, it will not work if this is present, because you can see that this is an odd function. I cannot have this if I have an odd function inside, it will not work. So in order for me to write this, I need everything inside to also be even. And that can only occur if your function is made of only even functions. So let me write it here. So this is even. Odd. So for this to be odd, sorry, for this to be even, this part should also go. And similarly, if this is odd, this will go and that will remain. Yeah, so roughly speaking, that is now here, if this is odd, this should go. Therefore, we have odd equal to odd, even equal to even. Right, okay, that is for your understanding concerning the theorem. So here it is if, this one is if f is even. Now, if f is odd, then we have this expansion. Okay, and the proof, I already told you, you can always prove that the b case, because it comes from this fact. If s is even, this b case will all be 0. The b case will be 0, so all this term will cancel out. Now, if it is odd, the a case will be 0. And this result comes from this lemma that I stated here. So if you use this lemma, you will see. Okay, let me write that. Let me use this lemma to show you what I'm actually talking about. Okay, so let me show this, because remember I said that a case, b case will be 0, right? Now, if so, we assume that f is even. So we are in the first case, this one. Okay, Now the next thing to do, and the simplest thing to do, is just to come here and to write our BK. BK, what will be BK? We know already that BK is equal to 1 by pi, the integral, negative pi to pi. Oh no. This is even. This is odd. Even times odd. So what is the result of even times odd? It will be odd, right? So this entire function, okay, let me write it this way. So this will be equal to the integral from negative pi to pi g kx dx, where this gkx is this product. We saw that it will be odd, so this is an odd function. Now if you look at the lemma, of course, even this factor 1 by pi, I can still take it inside, right? Because a constant will not change the parity of the function. Parity here means that it is even or odd. So those one I can still take it inside, or I can leave it outside, doesn't matter. Now, what will be the integral of this if I have an odd function center over an interval that is centered at 0? And the integral of an odd function, the integral of an odd function over an interval centered at 0. Let's look at the lemma. We say g is an odd function, and you can see that this integral of g is 0. So after this lemma, which I prove here, is 0, right? So this is 0. It's identically 0. So because bk is 0, it means that for f even, f of x will be this. And similarly, if f is odd, if this is odd, you can write the same thing for bk. Okay, let me write it. Because if I ask you to go and do it, very few. So let me write the case where f is odd, f odd. Now I can write my AK So here you have odd, even. So odd even is still odd. So you see that this integral will also give you 0, right? So odd times even is the same as even times odd, which is odd. So so after this, automatically now I can call this h sub k x dn. This is an odd function that will give you 0. Okay, good. Now, in terms of the structure, because we need to compute this A case for the case where f is even, and we will need to compute bk in case where f is odd. Now, how do I compute my A case? How do I reduce the computation of my A case and my B case in these two cases? Now, there's a second part of the lemma that I did not use. In fact, this one. This one. You can see that this one, we are going to use this for the remaining coefficient, the non-zero coefficient, we'll be using this. Because for that case, the function under the integral will be even for both cases. Right. Okay, now let me come back to this one. Okay, so I will take this one because I will complete the computation of this A case because the A case are the only coefficient here. And now I will take this. Yeah, I can leave it somewhere here. Now, how do I compute these AKs, these ones, when f is even? Now, AK is 1 by pi, this integral, cosine kx dx. So you agree with me that we are in the case where f is even, right? F is even. So here we have even. And this is even also. So even into even is even. So the final, the overall, that is this product, will give rise to an even function. Right. So this is what I call the below here hk, h sub k. So I can say this is one by pi, the integral from negative pi to pi h sub k x dx. Of course, where this hk is this factor, right? Okay, now if you look at the lemma here, because we know that this function is even, this hk is even, right? This is even. Okay, that's an even function. Now, if I integrate an even function over an interval center, you see, here a is equal to pi. Now, if I integrate an even function, f is even, it will be 2 times. Now, I will integrate from 0 to a. In our case, it will be 2 times integral from 0 to pi. So, because that function is even, I can just say this will be 2 times. Now, I will not start from negative, but from 0 to pi, and 2 times here. So, meaning that this will be equal to 2 by pi. You see, 2 times that integral from 0 to pi. Now, we will integrate from 0 to pi this function. And what is this function? Is this f of x cosine kx dx. So you see, and that this is what you have in the note. Okay, now similarly here, when f is odd, if you write the formula for bk, we'll have a similar situation. Now, bk here, we know it is 1 by pi, the integral from negative pi to pi, f of x sine kx dx. And this is odd function. And this is also odd. And we know that odd into odd is odd. So the overall function, this factor, this product, is an even function. Odd, odd, even. Even, even, even. But when the parity of the two are different, the result is odd. If they are the same parity, the product will be even, right? It's exactly like this. We know that if you have negative times negative, it is positive, right? And if you have, okay, they are the same, positive times positive, it's still positive. You can see that they have the same parity or the same sign in this case. Same, we have positive. Now, if they are different, if you have negative into positive or positive into negative, you see they are different, they will always be negative. So it's exactly the same thing here. If they are different, they will always be odd. Odd here is like negative, and even is like positive, right? Bear that in mind. So if I have odd, odd, like negative, negative is positive for even. So now you have
Doctor.
even. So you see that for these two cases, f even or f, the constant, the coefficient that will remain in my expansion, the integrand will always be even, and therefore it will always be 2 times. So similarly, as in the case above, I wrote, yeah, that one. So this will be equal to 1 by pi integral negative pi pi. Now this is what? This is g. G. Oh, sorry. G. Eh? How did we call that G? Eh? Yeah. Was it G? Yeah. That is G, but now G in our case, yeah, it's G. This one, this times that, we call it G. But G in our case is even, it's not odd, right? Because here you have two different parities here. Whereas in our case, this will be odd. You can see F is odd, so it will change. So this G and this is even. So because it's even, the result will be 2 times this integral from 0 to pi. So 2 times from 0 to pi. And then this function, and what is this function? I can replace directly by fx sine kx dx. So you see that all these results are not imaginations. They are results of okay, so we have our AK. You can see that the BK here is 2 times the integral now from 0 to pi. Similarly, here the AK is 2 by pi, integral from 0 to pi. Very important to know. Okay, now let us apply this. It was very important for us to go through this. It's not a waste of time because the experience from the previous years is that some people during the test, they cannot even write AK, BK properly. And once in a test you write the wrong integral or the wrong integrand, be sure that all your results will be wrong. You need to understand this in details. It's in such a way that if you have an even or odd function, you don't waste your time computing coefficient that you know should be 0. It will be a waste of time. And some people, even though from the theory it should be 0, when they start their own computation and through mistake or error, they will get a result that's different from 0, and everything will be wrong. They will have wasted their time, their energy, their money, and everything. Very important to understand these details, and once for all. Okay, now I hope things are clear when it comes to these things. I hope things are clear now for most of you. If not all of you, things should be clear, like what? Crystal. Crystal. Yes, crystal, I say crystal. Good. The next thing now I say application. So let's move to the application and see how to apply this. I'm going to share a new slide where we will see how to apply this thing. Okay, so you can see now here, as I mentioned, if the function is an even function, you can see that the BKs obviously are zeros, and the AK, you can see that is 2 by. And now we start integrating from 0 to pi. And similarly, when f is an odd function, the expansion will be only in terms of sign, right? And B, you can see BK is also 2 by pi, and now you integrate from 0 to pi. That's exactly what we covered. So there's no need for you to integrate from negative pi to pi. It becomes easier to start from 0 to pi and multiply the result by 2. Okay, now let us look at this particular example. Show that the function extended periodically by the equation has the Fourier cosine representation, this one. Okay. First of all, if you look at this function, if you look at this function, you can see that this function is an even function here, because you can see that we have an interval here centered at 0, negative pi to pi. If you look at absolute value, if you take f of negative x, which is still here, you will see that the absolute value will absorb the negative sign and it will be equal to f of x. So you can see already that over this interval, your function is an even function. So by extending that periodically throughout the real line, we will maintain the periodicity. I mean, not the periodicity, but I mean the parity of the function. Parity means that it is either even or odd. So it will remain even by extension. So the function is an even function, right? So you can use the theorem to state that this function being even here and extending it periodically on the real line, it will remain an even function. Therefore, all the bk's will always be 0. So from there, you know that your expansion will always be in this form. So you write this. You have to justify first, and then you write this. The next thing now will be to compute your A0 and the AKs. So you write the general formula for AKs, which is this one, from 0 to pi directly. You don't need to. Now this is where things become important. This is where things become important. You see the way the function is defined here. The function is defined with the absolute value. You have the absolute value when it is defined from negative pi to pi. But now, if you write from 0 to pi, you cannot keep the absolute value. Because you have this is global definition over that interval. But now, if you take from 0 to pi, you cannot keep the absolute value. You have to remove it, right, by the definition of the absolute value. So this will become x on the interval 0, pi. Now, what if you decide not to use this formula, but you still keep the formula from negative pi to pi without the 2? In that case, you have to express the absolute value in the interval from negative pi to 0, which will be different from this, from the definition of the absolute value, plus the integral from 0 to pi, which will be x. You have to bear this in mind, because if you don't do that properly, your result will be wrong. I repeat again, your knowledge of mathematics from high school, nothing should be left aside. All the knowledge should be used. Oh, because there will be no class for you on absolute value. There's something that was done, you use it, and you continue. Okay, so now let's come here. So my function, which is positive on this interval, absolute value of x will be x. Because of the interval. If I have the interval negative pi to 0, it will be different. It will no longer be x. So you have to bear that in mind. Otherwise, your result will be wrong. Okay, now you substitute, you apply integration by part exercise. So do this. Integration by part, similar to what we did last time. If you apply integration by part, you should be able to get this. And now the next thing will be to integrate this. I mean, yeah, you integrate, you get this. Now, how do you move from this expression to this? Because if you can't do that properly, you will not get the right result. Okay, but now let's assume that you did the exercise and you can see that this is equal to that. So exercise, do that. It's an exercise. Now, once this is found, you can see that this is true for any k running from 1 to infinity, which is actually, you cannot say k is equal to 0 because you are dividing by k. For the case k equal to 0, you have to compute that separately. Because if you substitute 0 here, you don't need to divide there. You don't need to reach here for k equal to 0. If k is equal to 0, your integral will be A0 will be equal to, here, you can even see it's here. A0 is 2 by pi into the integral from 0 to x, f of x dx, and f of x in the interval 0 pi is x. And then you integrate that directly, it gives you pi. So don't make the mistake to compute this and think that k equal to 0 is included. No, in general, you will separate k0 and k non-zero. In general, or almost all the time, that will be the case. Bear that in mind. Always split that, the case of a equal to 0, compute that separately and this case. Why should you do that? Because when you be performing your integration by pi, you always divide by k. And you cannot divide by 0. So that's why you always separate the two. Okay, now the next thing, this is interesting because if you look at k here, you see that for some values of k, ak will be 0. Because look at this, negative 1 to the k will be positive and negative, right? It will be 1. If it's 1, this will be 0. If it's negative 1, the numerator will be negative 4. So you have to separate those two cases into groups. So you group them. So now, if k is odd, this will be negative 1. But if k is even, this will be 1, and all the AKs will always be 0. So you group the case where AK is even, or when k is even. When k is even, all the, here, it's written here, you can see. This will always be 0 if k is even. So you leave that aside, you only deal now with the case where k is odd, because those are the terms that will contribute into the value of AK, because the remaining terms are 0. Now, for the case where k is odd, the numerator will always be negative 4, because this will be negative 2 times 2 is negative 4, always. So we have something in this form. But you can generalize this notation. To say that k is odd means that you can write it in a particular form. K being odd means that you can write k as so k being odd means that you can write k as 2p, for instance, minus 1, like this. Yeah, 2p minus 1, where p can be 1, 2, 3, up to infinity. And you can check, if p is equal to 1, you put 1 there, you have 1. So the numerator here, k will be 1. And 1 square is 1, and you have it here. So when p is 1, k is 1, and you have a1, and this is the value. In the denominator, it will be pi. Now, if p is equal to 2, you put 2 there, 4 minus 1, 3. And then it will be pi 3 squared, which is this case. When p is 3, this will be 6 minus 1, 5. Right? So k will be 5. Then you have a5 will be what? Pi 5 squared, which is this one. So, in other words, we can write the general case here, a sub k, which is sub 2p minus 1, equal to negative 4 by pi into 2p minus 1 squared. So this is where p, of course, runs from 1, 2, 3, up to infinity. So in our integral, we can replace, obviously, we know that this is a by 2, right? The constant term here is a by 2, a0 by 2. We know that a0 is pi, so it will be pi by 2, right? So a0 is pi, then a0 by 2 is pi by 2, which is this term. Now, the rest of the summation here, this summation, on a, k, cosine k pi, we replace k by this value because k, remember, we say we can write k as 2p minus 1. So we come back here, the numerator is negative 4, right, with this pi. So we can take this negative 4 by pi, this term, consider this factor. Negative 4 by pi is our factor that we take here. So when we split, we are left with 1, 1. We have negative pi by 4, which is the factor that we take out of the sum. And the remaining term will be this 1 by 2p minus 1 square. And that's where we put our sum, because this depends on p. And this does not, I can take it out. Now you can see that this is just a relabeling. This has been relabeled. P has been relabeled K. This is a dummy variable. So you can write P here, or you can recall it K. It doesn't change anything. Okay, so I hope that with this you understand what was done. Please go try to understand. Okay, so I'm planning a test, not next week, but the following week. And that test will cover everything up to Fourier series, up to here. It will not include this part, trigonometric polynomial. For now, we will not include this for the test that will take place the week after the next. Likely will be on Monday. I will confirm that on Monday. But be prepared already. Inform the other student that there will be a test. Test 1 will take place not next week, but the following week. And likely on Monday. Okay. I hope you enjoy my class. If you did not enjoy it, I really enjoyed it because it was really sweet to manipulate this Fourier stuff. Some people, they were dizzy as I was manipulating this, as if their head was also turning like this. But I don't think that was the case for you. You understood everything. It was so sweet. So have a blessed weekend. Have a happy maths weekend. God bless you and see you next time. Bye-bye.
Bye, sir.